Well, students, as an application of product space, let us discuss what is called the Bernoulli Trials. So we will be coming across this binomial distributions and all quite often in this course. So what is so let's understand first what is Bernoulli trial. Uh, So you have a sequence of trials, sequence of trials. Okay. So just if you recall, in the product space, we also had a sequence of experiments or trials, and each one is modeled by a probability space, right? So similarly, you have a sequence of trials, and this sequence of trials is said to be uh, a Bernoulli trials if the following conditions are satisfied. The first one is there are two possible outcomes. There are two possible outcomes. Say we will call it as H and T. It need not be head and tail. It can be anything, but generally we are very familiar with tossing a coin and seeing whether head or tail comes. So we will always talk from the head or tail context. But any experiment which involves 1 or 0 kind of output, you can attach Bernoulli ideas with that. The second condition is, so this is for each trial. Each trial, your outcome is either a head or a tail, H or T. It can be anything. Let me denote it as a success or a failure. You can think like that. Okay, so there is a success or failure. The trials are independent. The next condition is the trials are independent. It means the outcome of one trial doesn't disturb the outcome or affect the outcome of the other trials. Yeah, so that is the meaning. And the third condition is the probability remains the same throughout all trials. See, the probability of say probability of head, okay, of, and and therefore probability of tail remains same in all trials. Okay, it's not that once I coin my chance of head is say 0.2, next time when I coin the chance of head is cannot change to 0.7 or something. Well, if you take a biased coins, you need not have 0.5 as the outcome. So it's all these are the conditions which will designate a sequence of trials as Bernoulli trials. Okay, let's try to construct a product space for the Bernoulli trial. Um, Products space for the Bernoulli trial. Of the for the Bernoulli trials. Okay, so if you see uh, what is the sample set. So before that, let's take consider n Bernoulli trials. Okay, you can just imagine that you are just tossing a coin n times. Okay, that's a very good example, or the simplest example that you can think of as a Bernoulli trial. It need not be causing a coin. It can be anything which only gives you two outputs. One is success or failure. Okay. So, but whenever I talk about this, we will always keep head and tail and tossing a coin in mind and talk, which can be generalized to anything that we want within the conditions of the Bernoulli. Okay, so what is the sample space? Since you are doing n experiments, therefore it is the it's the sample set is S1 cross S2 cross and so on up to Sn, because we have n trials, the n trials we had, and uh, each Si consists of only two possible outcomes, which is either success or failure, head or tail, 1 or 0, whatever way you want to represent the two events, you can do that. So in that way, you have, so S consists of n tuples. This consists of n tuples. N tuples, say every S is Sn. Okay, so the elements of the sample set S looks like this. Okay, where each Si is either head or tail, depending on the ith tossing, whether you got a head or tail. So what is the sigma field? Sigma field is since it's a countable, in fact finitely many elements are there, you have uh, 2n possible outcomes. Okay, so we have 2 to the power n possible outcomes are there. Okay, so that is you can clearly see that, and so therefore you have you can take a power set as the sigma field. So that's there's no ambiguity in that. And what is the probability space? So the probability space can be taken as the discrete probability space. Okay, so discrete probability measure. Discrete probability measure defined as follows. Okay, so so let probability I of head, okay, be P, and therefore probability I of being tail will be 1 minus P. That is very clear. I equal to 1 to n. So the probability cannot change from one experiment to the other experiment. The success and failure probability of one experiment will be the same for all the other experiments. That is one of the conditions of Bernoulli. Okay, so therefore it's uniformly everything is P for success and 1 minus P for failure, or if you want to interpret as head and tail, it goes like. So from here we have to hook up the uh, general probability of the probability for the product space. Okay, so we have probability for individual probability spaces. Now we have to define the probability for the product space of all these probability spaces. So for instance, if we have KH and n minus k t in an experiment, in a trial. Okay, so one trial. Now as far as the product space is concerned, our one trial is actually the combination of n trials. As I told you in the last class, that is the aim of looking at a product space. So you have n different trials, you combine them and look all these not as individual trials but as one trial and take that as one single outcome. Then you have to look for a product space. That's what we are seeing. Therefore if we take k heads and n minus k tails in a trial, and in particular if that happens to be, if the outcome is h, all the components are h up to first k, k times, and then it starts from k plus 1 onwards tail and goes up to n minus k up to n, it goes with tail. Okay, so that's an element we have picked up, say, that is in our sample set. In particular, if the outcome is this, then what is the probability product product probability measure of our S is nothing but nothing but P1 of H, right? It's a product of this, right? Let me write like this. So first I is equal to 1 to K I, and then it goes with I equal to K plus 1 to N, it goes with tail, right? So that will be P to the power of K into 1 minus P to the power of N minus K. So that's the probability of one such element. Now this may not be the combination in which it might have occurred. It may be in different combinations, right? So therefore you have to take all the possible combinations which has k hits and n minus k hits into consideration. So some you have to brush up your elementary combinatorial analysis, counting procedures, all basics only. We will not use some very advanced ideas. A very simple school level combinatorial uh, ideas only we will use. So if you include all possible combinations of k heads and n minus k tails, then how many such combinations you can think of, right? So how many such elements you can think of uh, in S, which has k heads and n minus k tails, right? So let's call this as let h k be the event that there are k h's in the trial. There are n trials. You are you are tossing n times, and you got k hits. They may not appear in this order. They may appear tail, head, 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 tail, 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 head, tail, like that. In any order, they can appear. So therefore, you combine all these, all such outcomes into one event, and that is HK. Then what is probability of HK? How many such elements can be there? Obviously, there can be n k combination p to the power of k 1 minus p to the power of n minus k, right? So it's a very elementary combinatorial formula where we know what is nk. That is very familiar notation, is given by k factorial into n minus k factor. Okay, so these are the binomial coefficients, and this probability is called the binomial probability. Okay, so we started with the Bernoulli trials, and we have derived the binomial probability for it. So that's a very interesting and quite commonly used in application. Okay, many applications, and it's a good example of a product space that we studied in the last lecture. So let me give a simple example. Uh, so a telecom service provider. So next is an example. So a telecom service provider. So he has around. Uh, so at a time he can provide 15 connections, and he has 100 customers. He has 100 customers. The probability that a customer wants a phone line uh, at any given time is 0.1. Okay. And it is independent. So one person wants mm, phone line doesn't depend on anybody else. He decides, he or she decides by themselves. Okay, I want to make a phone call. It doesn't depend on any other customer of that service provider. That's an assumption. And now the question is, what is the probability that there are more customers needing the phone connection than the capacity? Okay. Probability of more lines needed than the available lines. That is more than 15 customers wants to make a phone call at any given time. Okay, so that's the question. So let's call this as suppose k number of people. Ck is k lines are needed. Okay, and now so at any given time, so you have what is that? You have a line is engaged or not engaged, right? So therefore, there are only two possibilities: whether a line at any given time a line is engaged, can be thought of as head, and not engaged can be thought of tail. Therefore, probability of CK is actually so how many customers are there? You have totally 100 customers, right? And how many lines are needed? That is how many customers who are seeking the phone connection. That is k customers are seeking the phone connection. And what is the probability of success? Okay, the customer given time then needs so the customer needing the phone line is zero point 0.1, and therefore k customers needs the phone line, and other customers doesn't need, so it's a probability therefore is 0.9, and that is 100 minus k. This many doesn't want the phone line at a given time. Okay, so therefore you need now what we need. So this is the probability. You give me any k lines, that is the probability. Now let C be the event that at a given time there are more than 15 customers, right? Want customers wants line. Okay, then what is probability of C? This is what we want to find, right? So what is that? That is nothing but you just uh, k equal to 16 to 100. So first 15 are okay, fine, they have no problem. And see, this is ck is the number of people wanting the phone line, right? That is the event. K number of people wants phone line is ck, and the probability we have already found, that is given by this. Okay, now more than 15 people means 16 people wants is probability P of C16, 17 people wants probability C17, and so on. So if you add them all, that comes to be the total, because the C will be the union of all these events CK, right? 16 C16 union C17 union and so on up to C100. Okay. They all are disjoint because at a given time, if there are say 20 lines wanted, then it cannot be 25 lines wanted, right? So 20 line means at that second 20 line, that's a C20 only. Okay, so therefore these all are disjoint. Therefore you can, when you take probability by countable additivity, you can add them up. And so once you have this, you can you will have to sum them up. Okay, you will have to sum them up, but what you can do is you can do a shortcut. This is nothing but 1 minus sigma k equal to 0 to 15 probability of ck, and that also is a little better than the previous one, but still I don't know, maybe I calculated by calculator or I don't know. So this is the answer final.